Hello everyone, I'm Himanshu Vasnani from Department of Mechanical Engineering and I'm here to discuss with you on the subject non-destructive evaluation and testing. The subject code is ME419, unit number 5 in the series, subject lecture number 34 in the series. Okay, and covered today's topic are effects of inspection conditions on eddy currents and the components of an eddy current system. The learning objective for today's lecture are to provide the students with a basic understanding of effects of inspection conditions on eddy currents and to know about the components of an eddy current system. And after the lecture, the outcome will be the students will have an understanding of effects of inspection conditions on eddy currents and students will understand the components of an eddy current system. Now, we have been discussing about eddy currents in the past lectures. Okay, some few terms that we need to discuss about this are that the cracks, liftoff, and connectivity. Okay. Now, the impedance changes due to the surface cracks of different path depths. The change of for cracks will lie between the liftoff and connectivity. So, as the crack depth increases, the response moves farther from liftoff and closer to decreasing connectivity. Okay, you can understand there is a response in this that as the crack depth increases. Okay, now here the response is noted that the response moves farther from liftoff and closer to decreasing connectivity. So here you can easily find out that the crack depth is increasing. Now, the crack detection in non-ferromagnetic materials. Now the amplitude of the response from a surface crack increases as the crack gets deeper. So when the crack reaches lead standard depths, it is interrupting essentially all of the eddy current flow, and no increase in amplitude is seen as it is gets still deeper. Okay. Now besides an amplitude increase for deeper cracks, the phase angle of the crack indication changes. A shallow crack interrupts little of the eddy current flow, so the amplitude signal is small. What they say, if you get a shallow crack, sorry, so a shallow crack interrupts little of the eddy current flow, so the amplitude of its signal is small. Also, it is essentially a surface condition, so the direction or the phase of the signal response is very close to that of liftoff. So you can see this in the diagram also on the upper diagram where you can see there is a shallow surface crack. And for a shallow surface crack, they say that a shallow surface crack interrupts little of the eddy current flow so that the amplitude of its signal is small. So you can see that you can difference between a shallow surface crack, how the liftoff is shown. Okay. Now, a deeper crack interrupts more of the eddy current flow, so its signal has greater amplitude. So just make it a point that if you have a deeper crack, it will interrupt more of the eddy current flow, and so the signal will have greater amplitude. So it extends, okay, well below the surface. The direction or phase of a signal is farther away from the liftoff. Now you can see in the diagram, in the deeper way, in the bottom diagram, you can see the deeper surface flow is there. You can easily understand by this that you can see the difference in the liftoff is shown. Okay, that where if it is a case of a deeper surface crack, then obviously the direction of phase of a signal is farther away from the liftoff. Okay, and if it is a case of a shallow surface crack, so automatically the direction or the phase of the signal response is very close to that of the liftoff. So in this way, you can easily understand it. The three standard depths crack has the greatest amplitude response, so it interrupts the eddy current as far down in the metal as the test can sense. It looks like a change in the bulk property of the lower connectivity and the crack signal detection, like this, or phase, this is on the connectivity curve. Okay, so this is again the shallow surface crack and the deeper surface crack, and you can easily see the difference in the liftoff. It is there, okay, in both the diagram. The difference in the liftoff curve. Okay, now, making the three standard depth cracks deeper will not change the signal response because there will be no eddy current flow for it to interrupt. However, there will be a change in the signal response for a subsurface crack. Now, first, the eddy currents will flow over the top of the crack at the surface, and the subsurface crack will not block as much of the eddy current flow, and the amplitude of the signal must decrease. Secondly, the crack is now farther away from the surface so its phase angle must be farther away from the liftoff. So you can see this statement. Okay, it is given in this the diagram. The two diagrams are shown. The upper diagram is showing the three standard depths of penetration. Okay, you can see the variation of the liftoff from the three standard depth of penetration. Okay, the three standard depth cracks is there. Okay, and you can see the symbol pi is shown. This is showing that standard depth of penetration. Okay, now in the bottom diagram you have the subsurface cracks, and they say that the crack is now farther away from the surface, so its phase angle must be still further away from the liftoff. So you can see the variation is shown that the liftoff. Okay, it is the crack is like away from the liftoff. You can see the orientation of the crack. Okay, in the bottom diagram, that is the subsurface crack. Okay, now signal response decreases as the depth of the crack below the surface increases. I repeat, signal response decreases as the depth of the crack below the surface increases. Okay, so as the subsurface defects get farther away from the surface, the signal amplitude gets smaller and the phase angle rotates clockwise away from liftoff. So you can see in the diagram also on the right hand side, obviously it is clearly shown. You can see the liftoff and how it is shown and where the deep surface crack is going. You see that as the subsurface defect gets farther away from the surface, the signal amplitude gets smaller. See, it is getting smaller. The liftoff graph is getting smaller and the phase angle rotates clockwise away from the liftoff. Now, phase lag at depth. Phase lag at depth. Now, a phase angle shift can occur and change the eddy current field time and travel distance. Okay, you can see the diagram on the right hand side. Okay, it is the diagram of phase lag and depth and part. Okay, on the horizontal axis you have the depth and part, and on the vertical axis you have the phase lag. Okay, you can see that is a line is drawn from the center. It is at 45 degrees. It is going upstairs, and various markings are done on the graph, on the diagram. So I discuss upon it. The changes at the surface of the part are seen immediately by the coil, where disturbances to the field at some depth in the part require some travel time to return to the surface where they are seen by the coil. Electrically, this is described as the phase lag at depth. Phase lag at depth, and the amount of phase lag is 1 radian, that is 57 degrees per standard depth of penetration. Okay, this phase lag from the liftoff, that is the surface signal, may be used to measure the depth of defects. The phase angle of a defect signal correlates to defect depth. Now, the effects of inspection conditions on eddy current. This was the very important topic. This is a very important topic when we talk about eddy currents. Okay, eddy current inspection. So, effect of inspection conditions on eddy currents. So, first is the frequency. Okay, the magnitude of the induced eddy current in the part it increases as the frequency of the inducing current increases. Okay, in turn, the higher intensity eddy currents which generate a stronger opposing magnetic field, reducing the penetration of the primary field. Okay. You can see in the diagram on the right hand side, you have seen that is the standard depth of penetration is shown. Now in the first diagram on the left hand side, the depth is less, whereas if you see on the right hand side, depth is more. And on the left hand side, you are given the high frequency and you have a low frequency on the right hand side. Okay, the coils are shown on the upper side as the name of test coil with AC is given, and you can see the eddy currents that are given in the workpiece that are going in the workpiece. So they say that the magnitude of the induced eddy currents in the part increases as the frequency of the induced eddy current increases. Okay. Now in turn, the higher intensity eddy currents generate a stronger opposing magnetic field. What happened? The higher intensity eddy currents generate a stronger opposing magnetic field, reducing the penetration of the primary field. Now here it is reducing the penetration of the primary field. Therefore, all other factors remaining constant, higher frequencies they result in shallower depth of penetration. You can see in the first diagram, it is clearly the statement holds true that when you have higher frequencies, okay, this result in shallow depth of penetration. And if you have low frequencies, they will result in deeper depth of penetration. You can say verified from the diagram also. So the magnitude of the induced eddy current in the part increases as the frequency of the inducing current also increases. So we have to be careful with that. Now the conductivity and frequency. So there is a relationship between conductivity and optimal inspection frequency. As an example, an eddy current inspection for cracks in aluminium alloy lesson 707536 with a conductivity of 37 IECS uses a frequency of 200 kHz. Now, this is a standardization that is given by the IECS. Now, to perform an inspection with comparable depth of penetration on a titanium alloy that is TI6EL4V with a conductivity of around 1% of IECS, a frequency of around 6 MHz would be required. Okay, so you can see the relationship between connectivity and optimal inspection frequency. So certain parameters are in consideration, and the IECS has defined some values for that. Electromagnetic coupling. Now, the interaction between the primary electromagnetic field generated by the coil and the inspection article is referred to as electromagnetic coupling. Now, because the field increases in strength with increasing distance from the coil, the resultant eddy currents at the surface of the part will also decrease in intensity. Okay, so you can see that the what do you mean by electromagnetic coupling? They say that the interaction between the primary electromagnetic field generated by the coil and the inspection article is referred to as electromagnetic coupling. There's a coupling between the both of them, the coil and the article. Now, because the field decreases in strength with increasing distance from the coil, the resultant eddy currents at the surface of the part will also decrease in intensity. Now, the fill factor. Okay. When an encircling coil is used to inspect a cylindrical shaped part, what we say an encircling coil is used to inspect a cylindrical shaped part, the degree of magnetic coupling is dependent upon the difference between the internal diameter of the coil and the external diameter of the part. What they say? When an encircling coil is used to inspect a cylindrical shaped part, the degree of magnetic coupling is dependent upon the difference between the internal diameter of the coil and the external diameter of the part. So this effect is termed as fill factor. What is fill factor? Now, for internal coils, the electromagnetic or inductive coupling is determined by the air gap between the external diameter of the coil and internal diameter being inspected. Okay. Now, fill factor is calculated with a formula, but in this case, the di is the side diameter of the part and d naught is the outside diameter of the coil placed in the part. Now the coil current. Now with all the factors constant and increase in current flowing through the coil results in a higher magnetic field strength. Okay. Now the temperature. The temperature is also very important when we talk about these things. Our temperature at which the inspection performed affects both the electrical conductivity and the ferromagnetic properties of the inspection article or the workpiece. Now they say that the electrical conductivity decreases with increasing temperature. This is a thumb rule which we are studying from the starting, that the conductivity of a workpiece will decrease if we increase the temperature. Okay, and the converse, that it is increasing with the decreasing temperature. That is the, we can say, the electric conductivity is increasing with decreasing temperatures. Okay, so the reduction at higher temperatures occurs because of the scattering of conduction electrons by atoms moving with increased thermal oscillations. So temperature affects on the ferromagnetic properties of a material are generally negligible, with one exception, as above a specific temperature called the Curie temperature, about 1400 degrees Fahrenheit or 760 degrees Celsius. That is for ferromagnetic materials properties. Ferromagnetic material properties disappear. Okay, so here in this they say that about the Curie temperature. Okay, now because of the thermal effects on connectivity, increasing temperature of the, you can say, inspection article slightly decreases, okay, of eddy, increase the intensity of the eddy currents at the surface of the part. Okay, what they say, because of the thermal effects of on conductivity, increasing temperature of the inspection article slightly decreases the intensity of the eddy currents at the surface of an part and slightly increases the depth of penetration. Now this is a link between, you can say, the intensity of eddy currents and then the depth of penetration of this. Now temperature variations also affect the inductance of the core. Remember, changes in temperature affects ET results. Therefore, during inspection, time should be allowed for a test system, and if the test part is stabilized to the ambient temperature. Okay, for example, the test would be to see if the part and the standard feel the same to the bare hand. Okay, into the bare hand. Now geometry. Now geometric features such as edges, curved surfaces, edges in thickness, and non-conductive coatings such as paints or surface affect the distribution and strength of eddy currents. Okay, so we say that the probe that is used in the eddy current testing is approaches an edge. The eddy current response is known as edge effect. Okay, what they call the edge effect? Well, because this is related to geometry, so this is discussed in the geometry part. And as the probe approaches an edge, the eddy current response is known as edge effect and appears similar to the response from a crack. Similarly, curved surfaces and non-conductive coatings can vary the distance between the probe, coil, and the part. Now, these changes are known as lift-off, and the consequent effects on the eddy current signal are called as lift-off effects. Okay, what they say? These are called as lift-off, and the consequent effects on the eddy current signals are called as lift-off effects. So lift-off usually cannot be completely prevented. Therefore, compensating for some lift-off is a part of the setup procedure. Now, part thickness variations can also produce an interfering response in some eddy currents units because the thickness is in range of the depth of penetration of the eddy current field. Now, the lift-off, very important thing, and you can see that on a diagram which is showing an impedance diagram showing the effects of lift-off. So here in the diagram also L is equals to lift-off, and you can see the diagram how this is lift off is increasing, okay, at a certain point, okay, and there are obviously the two materials, that is material 1 and material 2, okay, so you can see how the changes are done. So the effect of lift off can be used to measure coating thickness. What they are doing, they are used for measuring coating thickness. The changes in lift offs can be calibrated to allow measurement of non-conductive coating thickness. Okay. A fill factor applies to parts passed through an encircling coil and in a manner similar to liftoff. So they can be used to gauge some directions. Okay. So as say link between the inspection part is increased. What they say, now we're talking about the fill factor. They say that the fill factor it applies to parts passed through an encircling coil and in a similar manner to lift off they can be used to gauge some dimensions. Now as the test coil is moved away from the part increasing lift off, the coupling between the test coil and the inspection part is decreased. What happens? The coupling between test coil and inspection part is decreased, and the magnitude of the impedance change for a specific change in an inspection variable is also decreased. Now for prop coils, the dotted lines connecting points representing the some same material properties but with various amounts of liftoff have some curvature that is shown in this figure. Okay, now the line ABC, you can see the lines ABC. Okay, you can see the lines ABC represents the increased liftoff for one material. For material 1, the line DEF represent the increased liftoff for material 2. And the line from A to point D, it represents the increase in conductivity of material. So two components to material, one at one liftoff value. So liftoff between line BE, you can see the BE, okay, and CF are increasingly shorter, indicating the small change in conductivity. Okay, so you should understand this kind of thing. Now some eddy current equipment. Okay, the eddy current equipments are also very important. So we should have a general idea of what all eddy current equipments are used in eddy current testing. Okay, so uh, mostly eddy current non-destructive test instruments for field use are portable AC or battery powered units. So they are generally lightweight, okay, less than 6 lbs with batteries that provide up to 12 hours of operation. They have a liquid crystal display that is LCD or an electroluminescent display that is the clear. Okay, so they both have these kind of display that is with them, and the batteries provide up to 12 hours of operation. So some units have dual frequency operations with interchangeable display features. What does it? They have dual frequency operation with interchangeable display features. The newer effects, sorry, newer units have state-of-the-art circuitry with advanced microprocessors. Now frequency ranges to approximately 100 hours to 600 sorry 100 Hz to 6 megahertz for detection of large and minute discontinuity. Okay, you can see the range of frequency 100 Hz to 6 megahertz. Okay, so these units can be used to inspect first and secondly tracks, coatings, plate thickness, or secondary testing. Okay, but there is one more thing that the frequency range should be known to us. Okay, that is ranging from 100 Hz to 6 megahertz. Okay, for detection of large and minute discontinuities. So both kind of discontinuities they are can be found in this range only. Okay, and these units can be used to inspect first and second layer track, coating, plate thicknesses, and connectivity testing. Now some components of an eddy current system. Okay. Now in the simplest form, an eddy current inspection system consists of the following components. Okay. Like an oscillator, coil assembly, a bridge circuit, signal processing circuits, and an output display, a readout of speed. Okay. Now a block diagram of an inspection system you can see in the figure on the right hand side. You have this one oscillator on the top, then you have a bridge circuit, then you have the signal processing circuit, then you have the readout. Okay, before the oscillator, you have the test coil or test part is there, and then you do it accordingly. Now you can see that in this diagram, you can say with the coil applied to a test part. You can see this is the inspection system with the coil applied to a test part. The system may be constructed or for multiple purposes or for very specialized functions. In general, instruments designed for specific tasks such as measuring, coating thickness, or electrical connectivity are easier to calibrate and operate than general purpose instruments, but are also limited to their designed applications. Now, oscillator. Okay, now these are some components. One is the oscillator. So the oscillator provides an, you can say, alternating current of one or more frequencies to a test code. Now, the frequency used to determine the intent of the inspection and the material being inspected, the frequency is used for ET range from less than 100 Hz to greater than 6 MHz. So coil assembly, that is, we are now getting the flow. Now the coil assembly induces eddy currents into the part being inspected and detects changes in eddy current flow. So for some applications, a single coil is used for both functions. But more commonly, multiple coils are employed in assembly. So the common configuration has one coil inducing the eddy current flow and the separate coils uses detectors. So another configuration uses one coil as both an inducer and a detector on the test part. So in this way, they go with the coil assembly. Okay, so they give for the multiple coil assembly. Okay. Now you can go with the bridge circuit. So the bridge circuit converts changes in the eddy current magnitude and distribution into signals that are ultimately processed and displayed. So a common mode of operation is to have output of the bridge equals zero for a zero or non-flow condition. I repeat that a good mode of operation has to have the output of the bridge equals zero for a good or or non-flow condition. The presence of flaw or an other than good condition results in an unbalance of the bridge, thus producing a relatively small signal, and this signal becomes the input to subsequent circuits. Okay, now signal processing. Okay, the processing of the signals from the bridge circuit, it depends on the type of information to be displayed. A simple eddy current devices can be built that detect and amplify the signal or convert the signal into digital format. For example, a conductivity curve or a conductivity value. Okay. A more sophisticated system can process the complex electromagnetic signals into amplitude and phase and provide filtering to suppress unwanted signals. Okay. Now here, if you go with the output display, sorry, because we have discussing about signal processing circuit in our previous discussion, and now we are going to the output display. Eddy currents test data can be processed in analog or digital format. Now, some common output devices are meter readout, a strip chart, or an XY plotter, recorder plotter, and an oscilloscope display, or a video screen presentation. So, the meters are suitable for performing specific types of tests. Okay, requiring measurement of a single amplitude only. So strip charts for XY recorders and digital, you can say storage, allow the single trans amplitude to be displayed and correlated with some other parameters such as time or position. Okay, so they say that the certain things like strip charts or XY plotters and digital storage allow this the signal amplitude to be displayed. Okay, and correlated with some other parameters such as time or position. So eddy current instruments with a two-dimensional graphical display. I repeat, eddy current instruments with a two-dimensional graphical display are used where both the eddy currents are signal amplitude and the phase must be measured. These are the greatest common instruments available and they provide the inspector with the greatest capability to interpret the results. Now, output display obviously has a very role with key importance for the inspector because the inspector will detect the holes. Now, the eddy current subsystem. Now, eddy current the systems generally consist of three subsystems. One is the probe system. Secondly is the eddy current instrument, and third is the accessory system. Now, scanners and recorders are included with some subsystems and are considered to the accessories. What they say? Scanners and recorders are included with some subsystems and are considered to be accessories. Now, probes, so coil assemble. Now, eddy current probes. Okay, let's talk about coils designed to induce an eddy currents into the part being inspected and detect changes with the eddy current field. Okay. Now, a fundamental consideration in selecting an eddy current probe is its intended use. A small diameter probe of a narrow encircling coil will provide increased resolution of small defects. What they say, a small diameter probe or a narrow encircling coil will provide decreased resolution of small defects. Now, a larger probe or wider encircling coil will provide better averaging of bulk properties with a loss in sensitivity to small defects. Now, also the probe or coil must match the impedance range of the eddy current instrument with which it is to be used. Now, the probe shielding. Now, probe shielding is used to prevent or reduce the interaction of the probe's magnetic field with the non-relevant features proximity of the probe. Now, shieldings, not seating, no, shieldings. Okay, now shieldings could be used to reduce edge effects when testing near, you can say, dimensional transitions such as a step or an edge. Now, we have also discussed about this edge effects previously also. Okay, so when you talk about probe shielding, so probe shielding is also very important because you can say uh, we should avoid the interaction of the cross magnetic field with non-relevant features in close proximity of the probe. Okay, so the shielding could be used to reduce edge effects when testing near dimensional transitions such as step or an edge. Now, shielding could also be used to reduce the effects of conductive or non or magnetic fasteners in the region of testing. So, eddy current probes are most often shielded using magnetic shielding or eddy current shielding. So magnetically, the shielded probes have the coil surrounded by a ring of ferrite or other material with ferrite or other material with high permeability and low connectivity. High permeability and low connectivity. So, the ferrite creates an area of low magnetic reluctance, and the probe's magnetic field is concentrated in this area rather than spreading beyond the shielding. Okay, this concentrates the magnetic field into a tighter area around the coil. Okay, they say that this shielded probes they have the coil surrounded by a ring of ferrite or the material with high permeability and low conductivity. Okay, then the eddy current shielding uses a ring of highly conductive but non-magnetic material, usually copper, to surround the coil. Now the portion of the field. What happened? This portion of the coil's magnetic field that cuts across the shielding will generate eddy currents in the shielding material. What it will do? The portion of the coil's magnetic field that cuts across the shielding will generate eddy currents in the shielding material rather than in the non-relevant features outside the shielded area. So higher the frequency of current used to drive the probe, the more effective the shielding will be due to the skin effect in the shielding material. Okay, so we say that the higher the frequency of the current used to drive the probe, the more effective the shielding will be due to the skin effect in the shielding material. Now, classification of probes. See, probes are used in eddy currents and they are having very important. So, for that also we have discussed about this term known as probe shielding. So, now we go to the topic which is very interesting, that is the classification of probes. Now, while discussing this probe shielding, we have also came across that this shielded probes they have their coil surrounded by a ring or ferrite or other material with high permeability and low conductivity. Okay, so we should be going with that. That eddy current probes and coils can be classified by mode of operation or application or design. Now, when we talk about mode of operation, they say that there are three general modes of operation for eddy current coil. Okay, and now what they say that the assemblies like for absolute or differential or driver receiver, also called as reflection. So let's start with the first one, that is the absolute probe. So the most common type of eddy current probe is used in the field application is the absolute probe. Okay, now absolute probe consists of a single coil that is in contact or adjacent with the part being inspected. Okay. Now, since any changes in the area interrogated by the coils produces a response, the absolute probes can be used to measure specific material properties such as electrical conductivity and magnetic moment. What they say is since any changes in the area interrogated by the coils produce a response, absolute probes can be used to measure specific materials properties such as electrical conductivity and magnetic moment. So they may have other discrete electrical elements such as capacitors included in the probe, housing for matching to specific equipment requirements. Okay. Now the second thing is differential probe. Okay, you can see in the diagram you have absolute probe in the first thing and second is the differential probe. Now it contains two or more coils and are intentionally designed to produce a response when changes are sensed by the active only coil. Okay. Now, consequently, if the direct differential probe has two coils mounted side by side, gradual changes in the electrical conductivity or magnetic permeability would be sensed by the two coils simultaneously and no response would occur. On the other hand, if an abrupt change in conductivity should occur, localized to where it can be sensed by only one coil at a time, then there would be a response. So normally in both surface and bolt, whole differential probes, two small sensing coils are wound. What? Two small sensing coils are wound side by side in the shape of two back-to-back capitals D. Okay, now when they say that this is a kind of a differential probe, and they say that if you have normally in both surface and bolt hole differential probes, two small sensing coils are wound side by side in the shape of two back-to-back capital D. So they are wired in series with one wound clockwise and the other, or you can say, counterclockwise. So this produces an induction from a crack that defects first one way, then the opposite way, while producing little or no indication from conditions that affect both coils quality, like affects the coils equally, like lift off or connectivity changes. What happened there? That the producing this produces an induction from a crack that produces first one way, then the opposite way, while producing little or no indication from the conditions that affect both coils equally, like lift off or connectivity changes. Now, the third one is reflection probes. So these probes, this can have a wide variety of configurations, but all have a driver coil, wired separately from one or more receiver coils. So as probe with one receiver coil is called as reflection absolute, and a probe with two receiver coils is reflection differential. Okay, let's say that if you have a probe with one receiver coil, it is called as reflection absolute, and a probe with two receiver coils, then we should call as reflection differential. Okay, reflection differential. So reflection probes these generally deliver better signal to noise ratio, but are harder to make and therefore more expensive. The reflection probes are expensive. The fourth type of probe is known as remote field has two or more coils. So with the driver's coil being inspected from the receiver's coil, the remote field eddy current probes are used for deeper penetration into thick structures. Okay. Now the method of probe application. Now this is also very important when you talk about methods of probe applications. Now the eddy current probes can also be classified by the method of application. You can see in the figure that if you have a surface coil, how do you keep it? If you have an encircling coil, then how do you apply it? And then you have an inside coil, then also how do you apply it? So these are basic coil configurations in the diagram on the right hand side. Current probes can also be classified by the method of application. The most common application is the contact or surface probe that are used for flat or used for flat or relatively flat surfaces of a part. Okay, and say that the most common application is the contact or surface probe used for flat or relatively flat surfaces of a part. So eddy current probes used to encircle eddy current probes that are used to encircle a part are called encircling coils. And eddy current probes completely encircled by a part are called as ID coils or bobbin coils. Okay, then through transmission probes which utilize the coils on each side of a part, that is a sheet of aluminium for instance, is another method of application. Okay, so they say that eddy current probes are used to encircle a part called as encircling coils, and eddy current probes completely encircled by a part are called internal length or ID coils or bobbin coils. And through transmission probes utilize a coil on each side of a part like a thin sheet of aluminum for instance. This is another method of application. Okay, now all of these probe applications this can be operated in absolute or differential modes. Okay, you can see that two diagrams are there having the absolute mode and one is showing the differential. So you can see that there is a difference in the test coil. Okay, you have a difference in the test coil, you have difference in the resistors, you have distance in the reference coil also. You can see that there is a difference in both the diagram is there between absolute mode and differential mode. Now these eddy current probes can also be classed according to the shape of some very prominent features of the probe. Now, very thin probes are called as pencil probes, and probes with spatial electromagnetic shieldings are called as shielded or focused probes. Now, probes used in rivets or bolt holes are called uh, bolt hole probes. Now, certain types of probes with shaped ferrite cores may be referred to as E-core, U-core, pot or cup core probes. Okay. So we have been discussing about probes from very long. So I think that we should now discuss about MCQs in the current lecture. So the very first question of today's lecture is like phase angle measurements are a good way to detect a variety of flaw conditions. So decrease of conductivity, gamma cracks and permeability could produce the same single amplitude and it would be difficult to differentiate between cracks and normal permeability changes in a part. However, the phase angle of conductivity change is very different from a permeability change if the correct test frequency is changed. So what do you think? Is this the phase angle measurement is a good way to detect a variety of soil conditions? Is it true or false? I think it's true. It's true because it is a good way to detect a variety of flow conditions. Okay, so the answer is true. A. Our second question is the magnitude of the induced eddy currents in the part increases as the frequency of the inducing current increases. Okay, say that the magnitude of the induced eddy current in the part increases as the frequency of the inducing current. So in turn, the higher intensity eddy currents higher intensity eddy currents generate a stronger opposing magnetic field, reducing the penetration of the primary field. Okay, now this is something like very, you can say, we should listen to this statement point to point so that word to word so that you can understand the meaning. The magnitude of the induced eddy current in the part increases at the frequency or as the frequency of the inducing current increases. Okay, both are increasing. Now, in turn, the higher intensity eddy currents generate a stronger opposing magnetic field, reducing the penetration of the primary field. So, what do you think is true or false? I think it's true. It's true. It will reduce the penetration of the primary field. So, answer is A, true. So, the interaction between primary electromagnetic field generated by the coil and the inspection article is referred to as electromagnetic coupling. It is true. It is true. A is the answer. When an encircling coil is used to inspect a cylindrical shaped part. The degree of magnetic coupling is dependent upon the difference between the internal diameter of the coil and the external diameter of the coil. So this effect is termed as fill factor. I repeat, you understand. When an encircling coil is used to inspect a cylindrical shaped part, the degree of magnetic coupling is dependent upon the difference between the internal diameter of the coil, that is, internal diameter of the coil, and external diameter of the part. And this effect is called as fill factor. So what do you think? Is true or false? So I think it's true. The effect of fill factor, this is true. Okay, answer is A. Now for internal coils, electromagnetic inductive coupling is determined by the air gap between the external diameter of the coil and internal diameter being inspected. You can see that here, if you talk about the fill factor, it was different thing. But here now in the next question, they're saying that for internal coils, in the fifth question, they're saying for internal coils, electromagnetic inductive coupling is determined by the air gap between the external diameter of the coil and the internal diameter being inspected. Okay, so in this case, it's just true. For internal coils, it is true. Answer is A. The electrical conductivity generally decreases with increasing temperature and conversely increases with decreasing, you can say, temperatures. So I think it's true in this case. Answer is A. Now, the reduction of electrical conductivity at higher temperatures occurs because of the scattering of conduction electrons by atoms moving with increased thermal oscillations. So what do you think? Is true or false? The answer is true. A. As the probe approaches an edge, the eddy current response is known as edge effect and appears similar to a response from a crack. Similarly, curved surface and non-conductive coatings vary with the distance between the probe coil and the part. These changes are known as lift off and the consequent effects on the eddy current signal are called as lift off effects. So it is true or false? It's true. Okay, the lift off effects is true. Okay, answer is A. That is true. A. Now, temperature effects on the ferromagnetic properties of materials are generally negligible with an exception. Above a specific temperature, called the Curie temperature, above 1400 degree Fahrenheit or 760 degree centigrade, the ferromagnetic properties disappear. So I think it's true in this case about the Curie temperature. It's true. Answer is A. Now, the effects of liftoff can be used to measure the coating thickness, and changes in liftoff can be calculated to allow measurements of non-conductive coating thickness. So here discussing about liftoff only, then they say the effects of liftoff can be used to measure coating thickness, and changes in liftoff can be calibrated to allow measurements of non-conductive coating thicknesses. So what do you think is true or false? Okay, so we have discussed about liftoff a lot. So they said this effect of liftoff can be used to measure coating thicknesses, and changes in liftoff this can be calibrated to allow measurements of non-conductive coating thicknesses. So I think it's true. It's true. The answer is A. The answer is A. That is true. Now these are the references which you can refer and increase your knowledge in these topics.